So hi everybody, welcome to the RTOP and Radio Telescope Observation Party for this Sunday. And realize we're probably going to start having some kind of an East and a West Drake's Lounge, and maybe RTOPs if we get enough participation. The Australian group is, I think it's like 2 in the morning there, and even though they'll see the recording, we might just want to get an interactive one with them in their time zone. So that might be an early morning, session. So we might start doing that too, just because we have a pretty good group in Australia that looks like they want to work with us. I put together a compilation video. It's too long. It's an hour, and I don't want to keep you guys for an hour. But I'm going to start playing that, and I want you guys to be interactive with it. It's cut and paste from the various presentations from the East Conference, and I'm going to start with the talk about the sun observations. Then we got hydrogen observations and masers and pulsars, and from the various speakers, and some of the some of the key points I wanted to take from each of those that had something to do with observations. So feel free to stop and ask questions while we're doing this. I'm going to probably put in the post-editing the entire video, but I think you guys, if you want to stop and ask questions along the way, that'd be really fun. So I'm going to start playing it. I want somebody to tell me that you can hear the audio when I do it.
The sun is a thermal radiator and is actually not a strong radio signal. The sun is not very strong in radio emission. The reason why we see it so strong is because it's so close. It's only 8 light minutes away, and this is why it's strong. It's just close. If it were a little bit further away, we would just not see it. But it can be very nicely used as a test source. And there's this very simple setup possible, the itty-bitty telescope, which is quite a nice entry project. SID, that was mentioned in the introductory video, and there's more about it in later talks in this conference. So it's an indirect observation that was explained quite nicely in the video. It's the influence of the solar radiation on the ionosphere, which changes the rate of propagation path. And there's a project called eCallisto, again for observing solar bursts that observes in the VHF and UHF range over a wide frequency range. I have put some web resources on this slide, so anybody who is not familiar with that, just feel you should go to those websites and have a look there and see what you can learn about.
Okay, first, what's the IBT? It's our educational toy that's been with SARA for quite a few years now. I think way back, Chuck Forrester started us on that, and other people, Tom Crowley's kind of the main moving force now. But anyway,
I'm not sure why that's not advancing here. 1 second.
Educational toy that's been with SARA for quite a few years now. I think way back, Chuck Forrester started us on that, and other people, Tom Crowley's kind of the main moving force now. But anyway, there are some limitations in that. I'm trying to see how much of an instrument I can make out of it. So the things you run into, satellite finders around there, they give a good indication of satellites, but they don't really give a very good measurement of signal level. So I've considerably improved that. On the subject of pointing accuracy, I've done a lot in that area there. Ground noise, a little bit there. And next question, can we get some kind of calibration on the thing and not just have it kind of a little better than random number that comes out of it? Ready, aim, observe. For sighting originally, I had for daylight use, I had just a little chunk of fiberglass sitting with a magnet here, so that it wouldn't get broke all the time. And use the shadow of the sun on this piece for that. For sighting things at daylight, just sight down it, worked pretty good. But sighting the moon at night, because I was wanting to do some more serious moon measurements on it, it was really not very easy to see at night. So I went and bought one of the red dot finders like you commonly see on small optical telescopes with a little red dot on the sky. And bright daylight, the red dot finder wasn't any good, but the regular sights worked pretty good. At night, interestingly enough, the moon outshines the brightest red dot setting, and you could find anything except the moon, which is the thing I was wanting to find. So that kind of didn't work out either. The rifle scope I found was really the best finder for a moon sighting. It has a little reticle thing in it that you could either get a dark crosshair or turn on a switch and you get either a red or a green socket crosshair that you can change the level of. So no matter how bright or dim the moon is due to phases or whatever, you can still sight on it, because I wanted to be able to sight on the moon accurately and quickly aim on it, because I had run through 2 solar eclipses or lunar eclipses with this, making measurements. And one of the problems I found was I wanted to move off of the moon to get a background noise, background level, and then back on the moon. Getting back on the moon accurately and quickly was more difficult than I wanted. This proved to be the easiest thing. You do have to get used to where the exit pupil is on it, but other than that, it works real well. So aiming at the sun needs something, and a lot of people use the shadow of the feet on the dish, which is also a good way, but I already have this sitting out here. So it just made a little plastic screen there, put a black mark, which is, around the screw when it was aimed right on the sun. So now I can quickly aim at the sun, because the other thing I am wanting to do is some solar flux measurements on that. So that'll again allow me to go back and forth between cold sky and the sun more rapidly there. Then dish back lobes. First we had my experiment in July of 2019, which was in a presentation. When I put this mess of cardboard and aluminum foil behind the IBT, it resulted in about 7 degrees K lower sky temperature. So that was a pretty significant improvement in background, especially considering things in the background could be pets that move, people, other such things. So the 7K in the background is not necessarily stable. So anyway, that helped stabilize things. However, this thing you can see was held together with clothespins and fell apart. It's kind of a quick proof of principle, and I could put it on and off quickly to verify the thing. Or I said, I need something better than that. What's being done? And you always look at what other people have done. You don't want to reinvent the wheel. So we had Alex, as we just spoke, and he told us a little bit about how he had shielded around the dish, and you saw how significant improvements he saw on that. And so I looked at how he had put it on there, the 4 segments there, and I did similar. And then I looked at what Dr. Reeve and the group had done on the with a DSA 2000 thing. I think he's going to talk a little about the preamp stuff with us. But that is a very interesting shield to keep ground noise and out. As you look, it's kind of sculptured. It's not just a straight thing. And when you're making 2,000 of those, the fact that it's sculptured, costs you some money. And when you're making 2,000 of it, it adds up. So that was carefully optimized. And you look at the noise specs on that thing, and it is very low background noise. So besides having his super preamp in there, he's keeping ground noise out. So I'm hoping he presents some on that shield at a later time there. We'll see.
Anybody got any? Anybody else have an IBT, an itty bitty telescope that they have possession of and been actually using? Ted sounds like he has. I've got a when I was teaching bachelor astronomy, I brought one of those out, and it was very good to. In fact, it was during the daylight because that's when they figured they could give an astronomy course time in the day. But I'd bring that thing out and teach the students how to find the satellites, which is really designed for. And what that taught them is elevation and azimuth, and it also showed them how sensitive it was to humans. So you can point it at people, and you can actually see the increase in temperature, and get the if you set the alarm correct, you can get that. So it's very good demonstration system. Tom Crowley has been building the mounts for them that are rotating mounts that allow you to put a standard dish on there and then rotate it around nicely for demonstrations. He's also got the satellite finder interface to audio, so you can plug that into your PC with the sound input, and use Sky. What's it called? From Jim Sky, the Sky Pipe, and watch the signal go in. So that works very well, especially the modification to the satellite finder for audio. That is very very useful. Anyway, so that's the reason that's in the sun section is because that picks up the sun very well. You can easily just scan it across the sun, and you can see the sun, as well as trees, ground, various other quote hot objects. It's around 12 gigahertz, so it's more sensitive to heat, I think. All right, any questions on IBT? All right, so the next speaker is John Pettingale, who was showing the Super SID, and he's a hit on the YouTube channel. I don't know why everybody keeps clicking on him, but he's got almost as many as Wolfgang's talk for his Super SID, which was really sort of an off-the-cuff one. It wasn't even, he just sort of put it together to show it the video. He didn't even have it in the proceedings. So it was interesting how that dynamics work. So I'm going to show his real quick.
Right. Sunlight ionospheric disturbance is typically when we have a solar flare, you get an accompanying X-ray or ultraviolet radiation. Or alternatively, you could have a coronal mass ejection, which emits particles. So radio waves propagate by bouncing off the ionosphere, and any changes that affect the ionosphere affects the way the radio waves propagate. So if we continuously monitor a signal strength from a certain transmitter, then that transmitter power is always going to be the same. So any change in signal strength is due to changes in the ionosphere. And the Super SID monitor is designed to detect those changes. So a typical output from a Super SID monitor is shown below. We normally look from 0 to 48 kilohertz, and the radio transmitters in the US all cluster in around here. So some of those spikes are probably interference, some of them are actually transmitters. And what the program does is it monitors certain frequencies, which you set in the configuration file, and it just keeps a track of those frequencies and the signal strength 24 hours a day, basically. Plots them out every 5 seconds or so. And so a normal plot, when you put them all together to a single transmitter, you can see the signal strength is high overnight, dips down, comes to a sort of steady state during the day, dips up at night, goes up again. And so what happens when you have a solar flare is that normally flat distribution that actually has peaks in it, because it increases the signal strength from those transmitters, and that's how you detect solar flares.
So the SAM-3 magnetometer, the SAM.
Okay, that was from John on the Super SID. I've had a Super SID for about 5 years. I consider it one of my best radio telescopes. No fuss, no muss. You make the big square wire thing in the back. It's about 27 kilohertz. So if you realize how much wire that is, and then you plug it into your PC and you let it run, and it delivers data automatically to Stanford, so you can actually see it on the web, what your old reports are and everybody else's reports in the world. Hundreds of people are automatically reporting. You're able to see the solar flares very well. I was also able to see the eclipse when it came by, because an eclipse looks like a night-day variation, so it actually comes up and down and gives a nice signal in the eclipse. People are also looking for it changes the ionosphere reflection, so people are actually looking for earthquakes with it, seeing if the earthquake causes ionospheric shift somehow, and therefore would cause a reflection change. Various other studies people are trying to do with it. So from a starter, if you want to get some real good science information, it gives you good science. It's easy to use, great for students, especially when they can see solar flares. I go to the NOAA website and look up the GOES information, which also gives the solar flares, and you can compare that with the your data you're getting. So it's easy to verify that what you're getting is actually a flare, because you'll see it also on the GOES satellite site, and that'll be a good verification. Okay, any questions on Super SID? Nope. You guys can talk during this. This is fine. I'll edit out any bad comments. That's okay. All right. Let's see. So sort of solar related is the magnetometer, which Reeve has been producing magnetometers for years, and it does affect the aurora or the the sun affects magnetism, Earth magnetic field, etc. So he's been able to put together a magnetometer here, and he sells those things. I've actually got one.
Part of that is simple aurora monitor, and it originally was designed by a couple of my colleagues in Germany, and it was capable of running 1 or 2 sensors. And in early 2009, we had it. We redesigned it to use 3 sensors. So this now becomes a pretty good geomagnetic observation tool, because we can look at 3 axes or 3 directions, and then come up with the vector sum to tell us exactly what the magnetic field is doing. So it's a pretty good geomagnetic observation instrument. It's used by the Space Weather Underground, or SWUG, which is an organization of some universities that use it for public, for education and public outreach. And going back to its original design, it was a disturbance monitor for aurora photographers, and also for amateur radio operators, that when the SAM indicated a geomagnetic disturbance, they could point their VHF antennas to the north and use aurora reflections for communications at VHF. I mentioned that sensors are temperature sensitive, so they were moved into this new environment, and it took them a day or so. Actually, we recommend about a 7-day acclimation period before you start really wanting to get data. you can see that things pretty well stabled about 24 hours later. But this is the temperature effect here going in, being placed in the ground. It's cool down there. And then, so the sensor output drifts, and then it seems to stabilize a little bit. You see it getting a little bit noisier there. And that was because there was a storm brewing, a geomagnetic storm was brewing. And so the next day, on the first day of July, things were very quiet. And the next day, bang, right about 0300 UTC, a storm hit, and you can see that we had quite a bit of activity. And the temperature drifting is not nearly as bad as it was the day before. We normalized the magnetograms at midnight UTC, and typically if the traces start out at 0 like they're showing here, they'll end up in the neighborhood of 0 at the end of the 24-hour period shown on the magnetogram. And you can see there was a little bit of drifting yet, so the sensors hadn't totally acclimated to the ground 24 hours later or so. So we had that magnetically active day right after we installed the sensors. And that gave us a really good indication that everything was working.
Jupiter.
Okay. Any questions on magnetometers? I think the only thing is, I think one of the guys in California had one buried, and very sensitive to cars or any kind of metal objects. So you want to put this stuff, you want to get it buried. And he also had moisture problems when he buried it. So you got to put it in a nice PVC pipe that does not have, you want to get all the condensation out of it before you seal it. And you want to get it away from, metal objects like cars going by, because that'll affect it. So somewhere in a field somewhere that does not have anything going over it.
Did you say what they cost? What's the cost of these things? Maybe one axis.
I have no idea.
How large are they? How large are they, and what do they look like?
They're about this big. If you go to Reeves, he's got a picture of it.
So about 6 inches or so, yeah.
Yeah, that, and you bury it about 3 feet down, and then you have to have the cables running to, I guess, the receiver or whatever.
They were doing some magnetometer stuff in the British Astronomy Association as well, so that's another source. But I just wonder whether you can build them, or whether, is it a bunch of coils with an amplifier, or
it's a kit.
A magical part you go buy?
It's a kit with some magnetometers. It's, you have to put it together. I got the kit, but I actually gave it to somebody because they said they had time to put it together, and of course they never did. So I'm going to go get it back. But I don't think it was that expensive, and the kit does not look hard. Some assembly required, obviously. And he says part of his problem was, he put it out in a field, but the varmints kept eating the cable. Was his major problem. So he had to surround it, different ways to keep the varmints from eating his cable. We normally bury PVC, have a pipe with a loop, and then we bury the cable with PVC, a couple feet down, and that's how we keep our varmints off at the Haswell site. Let's see what else.
So I can make a couple more comments about this too.
Yes, go ahead.
The group, the science group that is working with Tapper, is also working on one of these sensors, and they just got some funding, and they're going to be building 250 of them to sell through Tapper. That in their case, their sensor is based on a solid state device that's soldered to a board, and they're going to use 3 axes, and they're going to have instructions and things on how to bury them, and they're looking for you to be connected to the internet and feeding your data back out to them. In the case of WIT, he's using a flux gate sensor, which is a device that's made by a company that's small. And from what I saw, they were like $65 to $100. I looked into this quite a bit myself several months back, and actually designed a PC board to use a coil, a series of coils instead. The problem with coils, though, is that you can only look at the change in magnetic field, not the absolute field. In the case of WIT's device and the one that Tapper's building, they can look at absolute levels, but it needs to be sensitive to pretty low levels. You saw in his data that he was showing you a field strength of like 400 nanoteslas, and that is a very low magnetic field, but that's also where he's located. And so in different places on Earth, you're going to see different field strengths. And I think you need to be sensitive down in the tens of nanotesla to really, be sure that you're going to have good coverage in your area. But yes, it would be sensitive to trucks and tractors and anything else that drives by. Some of the people in the UK talk about detecting their lawnmower, for instance, because they bury these in their backyard so they can see when they're mowing their lawn. So, but it is a very interesting project, and I think that the Tapper version will go fast. So 250 that they have will probably sell out real quick.
So how far away does this truck have to be? Is there any hope for a residential area, or is it you got to have a couple acres?
No, I think you can look at like maybe 100 feet or something like that away from you, but you still may see a bump in your data even 100 feet away if it's a pretty big truck with a lot of steel in it.
Thank you.
And I think the worldwide network, I'm not sure what their science goals are, but I think WIT's also tied in, his current stuff's tied into a worldwide collection scheme where they're trying to look at the worldwide magnetic field, et cetera. This would be interesting because of the magnetic pole shift people are talking about, whether if we can actually see any of that stuff with a worldwide set of sensors going. Okay, any more questions on magnetometers? Yeah, I think if you guys want one, see WIT or see the Tapper group, I think would be fun. Okay, so a couple things on Jupiter. We had a good intro from Wolfgang, and then we had Dr. Chuck Higgins, who's in charge of the Radio Jove 2.0 project, and gave some info on that. Also, by the way, the introduction, Ed's introduction to radio astronomy is also a hit on the YouTube. And everybody, the reason we have that as the first talk of the session is because everybody realizes that sets up the stage, the base for the rest of the conference, because it gives you the basics. And people always reference his thing. So he's on now, so you guys congratulate him for having another great video this year. Okay, I'm going to go with, start with Wolfgang, and then I'll go to Dr. Chuck Higgins.
As I mentioned, it's the only planet that we can observe as amateurs. There is a decametric radio emission due to the magnetosphere of the Jupiter. I won't go into any detail of that. You see the drawing here on the left. I am not going to explain that. I would recommend you to go to the website to learn more about it. The interesting thing in particular is that the moon Io has a very significant impact on what Jupiter does in terms of radio emission. So it's a scientifically quite interesting thing. There is a program, Radio Jove, which is intended to observe that, and it delivers receivers and so on, which we'll probably hear more about it in the later talk.
You've heard some radio burst yesterday. I'll play this one real quick here. This is a nice solar burst that we got from Tom Ashcraft out of New Mexico. And I know some of you know Tom. He is quite an excellent observer for Radio Jove. He does a lot of photography. He does Sprite. He's a I guess worldwide known Sprite observer. So the above cloud lightning discharges. He's had a really nice write-up as a NASA citizen scientist and an artist as well. So he's one of our best observers. So this is a recent solar burst with our some of our Radio Jove equipment. Here, I'll just play this real quick. A little more muffled than I expected there, so I apologize for that. I'm probably having some crossovers between my mic and some of these sounds here, but this is a spectrograph, so frequency time plot of, and you see here type 3, and it looks like maybe a little bit of type 2 followed these type 3 solar bursts. And on the right is the single frequency Radio Jove 20 megahertz plot of the same solar burst from Dave Topinski down in Florida. The audio was taken at 20 megahertz, by the way. The audio you probably didn't hear very well, but so that's a lot of fun to let people hear, audibilize some of these radio signals so they can hear the sounds of some of these. Sorry about that. Some of these signals, and you heard this from Ed yesterday on the Jovian burst. I'll just play this real quick. Let's see if this one goes better.
Following is Jovian S burst activity.
Again, I know most of you've heard that before, but and as Rich mentioned, that's what I do. Is I mainly study Jupiter and its radio emissions, and you can see the cartoon there on the right showing you where the locations of the emission regions at these decametric frequencies, the DAM. Emissions. So these are similar to auroral radio emissions. So this is spiraling electrons in magnetic fields, and those electrons either come from solar sources or, as many of you know, the Io related emission comes from the plasma generated. Essentially, the gravitation melting the interns of Io, which then causes volcanic activity, spews neutrals into the magnetosphere, which then get ionized by the solar UV, and now you have this giant plasma torus, and those field lines, that magnetic field lines from Jupiter that run through that torus, then will creates an electrical connection between the two, and so you get extra electrons sort of moving along those field lines, and those generate radio waves given the right conditions.
Another thing I don't want to talk about, but
okay, that's the quick Radio Jove part. Anybody with experience on Radio Jove? The okay, D says has had one. I've actually got an S. I've got the. I've seen those radio bursts. What you do is you go to. Well, one is in the journals. We've got the applications for the Radio Jove 2 receiver. Highly recommend the spectrograph version of that. The old Radio Jove receiver. The nice thing about that is it was also a sort of a soldering kit. That you actually build your own receiver for 20 megahertz, and then you plug it in, and the antenna. I got laughed at because I was using the wrong too light of a PVC by my group. So they at Haswell they put steel pipes up, 20 feet. So they overdid it, but you can actually make the antennas pretty well. It also shows your phase. It does a phase angle compilation. You put a delay in one side, and it'll actually phase the signal down so you can see Jupiter, because Jupiter changes angles in the sky, in the southern sky, over the year. So in order to see it correctly, you need to put a phase delay in. I think the forward. I think it's the forward beam. Or you have two dipoles, and you put a phase delay in that one. So it's very interesting. You can learn how to do phasing with that, and obviously if you get the go to Radio Sky website, it actually has Radio Jupiter Pro, which shows the predictions of when these bursts are going to show up. So you don't have to sit there and just keep it going. You can sit there and just turn it on in the time frame of those bursts and receive those. So very fun project. Also very good for students to learn how to do that, and is actually good science because it's the only planet really that you can pick up radio signals with. So all right, any questions on Radio Jove?
How small of a system could you set up? What would be the minimum size of an antenna?
I think it's a 220-foot dipoles on and they got, if you go to the Radio Jove website, they got a antenna guide how to build one, and you basically have them, I think 10 feet apart. They're 20 feet long, and you have them up on PVC poles, or you can have them higher. Higher is better, obviously, and so it's not hard. It does take a footprint in your yard, but it's pretty fun to put together. Yeah, this is not a rooftop project. This is you got a small field, on the side. But yeah, but it's easily. Go ahead, Mike. Yeah.
Why don't they use ham radio antennas, like beams, like a 15-meter beam?
You can. People do, and they use pointing at it. Use it for pointing. Yeah. Jupiter moves across the sky like the sun and the moon and all that kind of stuff. So it does change elevation. So when they got these two dipoles, is just basically you're aiming it south, and you're picking it up as it passes by. Some people use the hams can use obviously a bigger a Yagi, but a big Yagi, usually 2-element Yagi, for 20 megahertz. But yeah, you can. I actually picked it up on my wire when I was doing mine. So at a single wire, you can pick it up at 20 megahertz. Just depends how sensitive you are, and how big the burst was. But yeah, I picked it up on I used my ham radio at 20 megahertz to pick up Jupiter. All right. Mark, does that answer your question, Mike? Okay. Let's see. The next, I only had one clip on meteors. This is always a fun one, and it was from Wolfgang again. But our own Chip Savicki, our webmaster, has a site, I don't have the link to it now, but he has a meteor site. And then there's lots of meteor sites around. This is also another one that, Ted has at Little Thompson Observatory a meteors system.
Not very extensive. It's mostly listening in on 50 megahertz or so. Mike Odie online has done much more.
Yes, I have.
Okay, Mike, go ahead and give us some feedback on that.
We have been struggling with having analog TV stations. And here in the Midwest, we actually are lucky because we have some Canadian stations that are available. It takes a relatively strong station to get good echoes on meteors. And the premise is the TV station broadcasts, and the meteor, as it travels between 50 and 100 miles above the Earth, reflects that wave because it's being ionized, it's being burned up. And that reflection comes back down to the Earth, and you receive it as a ping. So, and I really enjoy it. It's something you can sit there and just be mesmerized by. I use a SDR receiver with a TV preamp. So the SDR receivers are not real sensitive, so that's the reason it needs a TV preamp. I've received them just on dipoles, but normally I run a 5-element beam, mainly so I can aim towards where I want to receive. And that's not the TV transmitter. That's perpendicular to where the TV transmitter is at. Okay, that's enough of that.
Great input.
I thought it was fascinating to see a plot of the activity over a whole year, and you start to see the showers pop up. I thought that was kind of neat too, not just the live images.
Can I add some to this also? I have a camera that I put up that's a Sony camera that you can order from China for about $30 or $40. And there's a group, again, in the UK and all over the world, actually, that is doing this. And there's some software that they put out that runs on the Raspberry Pi, and it collects images from the camera overnight. And I've had this camera running now for 3 or 4 months, and it gets like anywhere from no meteors to 50 or 60 meteors with a 6mm lens on it. So I'm looking at one patch of sky. Last night I got 59 hits. Now, some of those are airplanes. It does a pretty good job of filtering airplanes out, but sometimes it doesn't get them all. And one of the things that I want to do is eventually add the radio aspect of it so I can correlate the two together. But the Perseids meteor shower is real active right now, and that's why I got such a large count last night. And in their software, it takes you back and shows you like a picture of the universe around the Earth and shows you what meteor group these meteors are coming from. It looks at the trajectory of the meteor. Ideally, you'd have 2 cameras, and in many places they have that. And there's another ham in Plano, Texas, here near me, has a camera, and we're going to try to have our cameras coordinated. And with the 2 cameras, you can track these things and hopefully end up with a fireball, and you can take off to go find some pieces of the meteor that make it to the Earth if you're really lucky. But anyway, it's pretty fun to see this. You're excited. Every morning you go and look. How did the sky look last night? It gives you a composite picture. Or you can look at movies of the things coming in. It's a pretty cool deal.
Did you got a link to that,
yes.
that camera?
No, I don't have one yet. One day I'll do that too, though. Maybe somebody else on the group here has got one of these cameras too, I guess. I can put up a picture in a little bit.
Yeah, Bob, we're looking for a web link. That would be great.
I have two Sky cameras, and I use a program called All Sky with an E at the end, and it detects meteors and points them out to you, creates kilograms of the sky, and video and pictures of everything that flew over your house. So I'll put a link. It's a fantastic program, and it works on Windows.
Great.
Okay, Rich.
Yeah, Mike.
I also have a video camera that I've been running for 12 years. And I've been collecting meteors on the video camera. It's aimed at the zenith, and it runs on Windows 98. It's a program called Metric, and it's was built by a German guy, Circle Malay, and that's part of the IMO, which is International Meteor Organization. So every night in the morning, I have 10 to 50 meteors to look at and decide if they're actually meteors or airplanes or birds or bats or bugs. So it's a lot of fun. I've collected a lot of meteors over the years. I've only once actually saw a meteor on the screen and heard the ping at the same time. So I got one coordinated RF to video. That's it.
Great. That sounds like a write-up in the journal. Just saying. Okay. Any more questions? Let me get let's just say what figure out. See what Wolfgang had to quick say about it.
So a brief slide is meteors. We have learned that this is a reflection of the ionization trail that was shown in the video with a nice graph. So the essential scheme is that meteor enters the atmosphere, it ionizes the air, radio waves get reflected, and all of a sudden you hear something that you are not able to hear otherwise. This is a very, very active area of people. If I look at a German news or forum about radio astronomy, the vast majority of the posts are about this, because it's very interesting in the sense there's something happening. It's a dull object that remains the same. It's really something something up. There are active phases, that's active phases. So interesting subject. I now switch over to what I think is a very interesting and fairly easy way through emission, the 21 centimeter line. I call this my number one for everybody who wants to enter radio astronomy, and also that can keep you busy for a long, long, long time. Why is it good for beginners? It's fairly easy to build. There are a tremendous amount of options yet you have for us, and it's very simple. You can bring a lot of hydrogen. You can how to instrument and how to opt. There's a lot of interesting physics involved, and we'll come to that. Just as a reminder, the 21 centimeter line of hydrogen is a fairly simple process, essentially. You have a hydrogen atom, which consists of a proton and an electron, and this has two states that the atom can be in. The proton and the electron spin can be parallel, or it can be anti-parallel. Now, The antiparallel situation has a slightly lower energy, so you have to put energy into the atom to go from here to there. And once it's in excited state, it drops back to the lower energy level, and the energy difference is emitted as a radio emission or a photon of 21 centimeter wavelengths or 1420 megahertz. The next interesting experiment, so one step up, is to do the classical experiment, look at the rotation curve of the Milky Way. Here we have, again, a similar drawing, similar scheme. Many spectra taken, but in this case, it is always looking at the galactic plane. So in this case, it's with a movable dish, which always steers at the galactic plane. And we scan in galactic longitude. So we have galactic latitude 0 and galactic longitude as far as we can see it from our location. And we see again how the hydrogen intensity and velocity distribution changes. Now, how do I get from there to the rotation of the galaxy? The scheme is that you don't need to take so many spectra. The idea is that you evaluate what is the highest redshifted velocity that I can see. And you do that up to the galactic longitude of 90. So maybe you take these number of measurements and look at the spectrum and look what is the highest velocity. Now, what do you do with that? There's something called the target point method. And again, this is something which would probably take 20 minutes to explain in detail. So I have to skip that a bit. The basic idea behind that is that if I'm looking a certain direction, the highest velocity that I will see is the part of this hydrogen cloud that is moving exactly in the direction of my where I'm looking, in the same direction. So it's moving away from me, but exactly in the line of sight. And that allows me a simple calculation of how far is that cloud away from the galactic center. As I said, it's called a tangent point method. I can't, for timing reasons, explain that in detail in this overview. What I suggest, but there are many explanations of that. I have listed one here in the below a web resource that you can have a look, but there are others. If you put in tangent point as the search in Google, then you will get a number of explanations. The basic thing here is that I can, with the help of that tangent point method, determine the velocity, the rotation velocity of the galaxy as it varies in the distance from the galactic center with my measurement, which delivers me two pieces of information. One is the galactic longitude I'm looking at, this angle. That's just where my telescope is pointing, which I should know. And then the maximum velocity that I have measured. And then I need to throw in two more parameters. One is the distance of the sun from the galactic center, which can be taken from literature, and the rotation of the sun around the galactic center, which is also a literature value, which is not determined by your measurement. And then you can draw and plot your relation here. What is interesting about that, and still puzzling, is that it doesn't drop. If you look at the rotation of our planets around the sun, that drops. The rotation speed goes to the outside. With these constant, more or less constant rotation of the galaxy when it goes out, that means that there have to be gravitational forces that are bigger than what our stars or the collection of stars in the Milky Way can produce. And that is a mystery still. It's called dark matter, something that nobody knows what it is, at least not by now. And you, with this experiment, you can demonstrate a basic physical problem or a problem of astrophysics of these days by your small telescope, saying, okay, I see the rotation velocity. And that is quite an interesting point, that you can do basic physics, or at least the basic physical questions, with your small amateur radio telescope.
Okay. There's also another video we put out with the this method on there that you can see, and also I recommend going to Wolfgang's video, and there's a lot of stuff I cut out of that about how some of the receiving for the hydrogen was, but we have a lot of good speakers. Charles has a compared various size dishes and horns with using hydrogen, and then Alex had a fantastic thing on how he actually converted the scope in the box to a very high precision system, and he was able and showed how he made the velocity corrections with it, which is very nice, because now we're getting down to analyzing the data stuff, which I think is more fun, because once you collect it, a lot of people quit on, hey, I collected it, hey, you know, success, and then let's go do something else. But the fun, I think, is in actually taking the data and actually showing that you got results, scientific results with it. I think Alex did a great job on that. So we'll start here with Charles, and then we'll go to the next one. Any questions on the galactic rotation rate? And by the way, you can actually calculate, if you know the rotation rate and the distance, you can actually calculate the mass of the galaxy with it too, which is very accurate when we did it on that one YouTube video. Any questions? No? Okay.
Radio eyes. I use radio eyes to be able to see where these dead zones are, that I can do the the IF averaging background in. So that works pretty good. Look for something that's less than 18 Kelvin. Stellarium, I won't talk too much about that. It works great. I use it to figure out where I'm pointed, kind of as a viewfinder, zoom in on that telerad mode, and it gives a lot of the information about what you're looking at any given time. Gives you the galactic coordinates and stuff too. Alright, and takeaway from this is you can actually set the scope in a box beam width and attempt to see what might be in the field of view. And I found that it was more like 40 by 50 degrees per scope in a box. So it's a pretty big chunk of the sky that you're averaging together. Okay, there's a couple of pictures from scope in a box versus 3.7 meter going through 100 Kelvin area. And I find the weaker areas of galactic ridge have a lot more interesting stuff than galactic center, where everything looks kind of lumpy. Okay, and here's a couple more comparison shots. Some of the spurs I see once in a while, those are kind of transient.
More analysis. Whoops. This was the last cool 24-hour clear day, nice weather this year. It was the end of March. And over a 3-day period, I acquired 4 samples of data. And I want to go through the analysis of this one particular 8-hour chunk. And what I did was I took 8 hours worth of data equated to 102 or 3 averages. And so every 5 minutes, every 1.25 degrees, I acquired a sample of data. And so I had 101 of these over that time slice. Process this in MATLAB because the 120 samples, would have been a monster to try to deal with in Excel. This is what the raw data look like. I'm still not sure the source of this drift. This is raw sample data, so I don't even know what this level is, but it went from about 5.7 to 6.2. So I don't know if this was temperature drift of the amplifier, whatever. What I did was I wrote a software script that I said, okay, I want everything to be as quiet as the lowest level. I averaged 50 samples here, and I corrected all the data. So I forced everything to, and equated this to 0 dB, so that all of the data is relative to that point, away from any H1 variation. This should be cold sky background. So this is normalized, referenced to a common point. Now all I had was drift in frequency due to local standard of rest, the variation, the rotation of the Earth and the position in which it's pointing. And go through this in a little bit more detail, but hopefully you can see these peaks are shifted where these are all pretty well aligned. Local standard of rest. The big monster is the rotation of the Earth rotating in, the Earth rotating in and out of its orbital velocity. Its orbital velocity is about 30 kilometers per second, so you can vary between plus and minus 30 kilometers per second every day. And halfway around, you are perpendicular to that, and so you get 0. And so this is 8-hour period. Over a 24-hour period, you are going to get this sinusoidal cycle, which combines, it's primarily due to the rotation of the Earth, the orbital velocity of the Earth, plus its rotation. And local standard of rest is the mean motion of material around in the vicinity of the Milky Way. So I'm not moving. How is everything else moving relative to me? I'll show you how I got this. I found an online calculator that allows you to enter in the time, the date and time, the location in the sky, hour angle declination in which you are observing, and your location on Earth, and you can calculate the rotational velocity. And so over that 8-hour period, I did this for 8 or 9 different times, and I entered these red values into Excel, and it came up, I used the second order curve fitting, and it came up with this equation. So I used this in MATLAB to correct all the data. It's a little bit difficult to show, but over that 8-hour period, the original drifted in frequency due to going in and out of Earth's rotation. And after correction, everything was pretty close. So this allowed me to create the second order equation, and that's what the data looks like corrected. So what this really looks like is corrected for local standard of reference is this redshift velocity. And so as I go through the Milky Way, I wound up with this spectrum. And what I wanted to show you, this probably makes more sense in that this was a velocity, let's see, I guess that's that's a red shift down to a blue shift. So the amplitude correlates to the color. So over that 8-hour period, the Earth's axis the Earth's axis is tilted 6 degrees to the plane of the Milky Way. And so over that time, you swing through the plane of the Milky Way. And that's what this is showing. This is showing above, through, and then on the other side of the Milky Way. And this correlating to a galactic longitude of around 80 degrees. And we're looking through the Perseus and outer arms. I presume that correlates to these frequencies. As an interesting check, I had corresponded with J.J. Mantois, And he has a map on his website that looks like this, that covers a large extent of the Milky Way. And I was amazed to find that this little 1 meter telescope had a very high correlation with what his spectrum, what he obtained with his 3.3 meter dish. And for looking at 3 different areas of the Milky Way, it's just surreal. It's just amazing that I have been able to get this kind of data with a 1 meter telescope. So I am extremely pleased that this correlates so well. So anyhow, last August, this is what I started with, and now we're up to things that look like this.
You by adding some oxygen to the hydrogen, and we have OH.
Okay, we got Alex online. It's your chance to ask him some questions. Alex, you got any more feedback on that? And any what's your plans for making a better antenna or doing more surveys?
Well, I've been working on.
You're muted.
Oh, so I am. So I've been trying to duplicate the loop, and then also across the room I have a patch feed, and I've been trying to tune these a little bit better than the original. But what I'm finding is they all seem to work pretty much the same. So I want to go through the hardware one more time, since it's so miserable outside right now. 2 hours is about the max I can endure, and get the hardware as well configured as I can, and then in fall to acquire more data.
All right, great. Well, great work on the on that itty bitty telescope, or not, excuse me, the on the scope in the box. I think that's people are gonna start improving their system based on your setup.
I really like the way you thought it all through, and then you spent time trying to understand the physics of it, and did a really good job of doing all that correlation, and then comparing your results to someone else and got good results. I thought that was a great job.
Thanks, Bob.
Anything else? Okay. Wolfgang also had a comment about masers that we'll just keep going on. And sorry, I'm trying to find my.
OH is a radical, so it's an incomplete molecule, desperately looking for yet another H to form water, but there's no other hydrogen available right now. And this OH has 4 transitions in the L band, so in the region where typically our hydrogen equipment works, at least close by. These 4 transitions, they can be observed in emission and absorption, but really what's most interesting for us in the amateur arena are OH masers. And these are circumstances where you have a strong infrared radiation, which excites the OH to a high vibrational level, and then it decays, and then it starts to getting a inversion situation, inversion between the different levels of the hyperfine structure, and then it starts to maze. The nice thing about OH is that in most cases you will be able to use your equipment that you have built for hydrogen. You can use it for OH emission as well. You may have to change the filter if you're using any, but that's all you need. Typically, the LNA and so on will be wideband enough, and also the SDRs will cover that. And there are a few examples which I want to show with 3 meter dishes. That's the sort of the size where you can do these kind of observations. The 3 on top are done from with a 3 meter dish from Eduard, and there are what are called circumstellar masers, so they are around a big infrared star. So the infrared radiation from the star generates the energy which makes them a maser. Okay, pulsars is our next subject.
Okay, masers. Anybody else do masers? That have some comments on masers? No. Yeah, I think that's it's a low-hanging fruit. I think that if you've got a 3-meter dish and you've already got hydrogen on that, and you want to do something different, then I think you can actually use the SDR and just tune it up to the 1600 megahertz, and then try for masers, which are a lot. They're not as bright, and you need a lot more. Need to work with it a lot more than the hydrogen, but it does look like there's a good sign there. That stuff is pulsars, and Wolfgang is we're part of a group called the Neutron Star Group, run out of Australia, who keeps track of all the amateurs that have been doing pulsars, and Wolfgang's Astropeeler group has 130 plus pulsars, and the Deep Space Exploration Society now has 22, currently being led by Dan Layne. So we got talks from both of them. But so we'll go through that, and we'll look at how do you set up for pulsars.
I think most of you will know what a pulsar is. So it's a pulse emission originating from neutron stars. They're typically strongest in UHF range, but L-band is also okay, I would say. Where many of us are operating. It's a weak source, essentially, 200 milliansky. Comparing that to what I just said earlier, I need 100 Jansky and more. How can I do 200 milliansky? Well, that's because it's this repeating pattern, which I can exploit. And they have a specific subject, which is dispersion. It means that if I observe over a certain frequency range, the arrival time of a pulse varies with frequencies. The higher frequencies arrive earlier than the later. So what I need to do is to correct for that. This is the same thing corrected, de-dispersed, and what is a completely smeared out pulse here becomes a sharp and nice pulse. Okay, so if you want to do pulsars, what is on your wish list? You want a large collecting area. No big deal, yeah. As big as you can get. You want a large bandwidth to collect as much energy as you can collect. You want a tracking system because you want a long integration time, and you want to observe in the band with the highest flux. So that's your wish list, but there are trade-offs. The observing band, typically the UHF is not that good because of the RFI situation, and the antenna size plays a role. A certain bandwidth, at some point I need to have definitely the need for de-dispersion. A tracking system, it's cost and effort, and collecting area, of course, is how much space do I have, can I still track, and so on. So I have to make compromises, and there.
I'll finally get to what we were doing there with our data in Haswell. This is the 60-foot dish. Everything is on GPS. We have a network time machine there for synchronization. We use Linux, so it's a System 76 Ubuntu 20.04 host. And everything I'll be talking about in here was either collected with a B210 or someone with the N210 SDR. There was 3 different feed horn configurations. One was at 408 megahertz with this LNA, and the filter was at 90 megahertz. We currently have up to 1296 megahertz feed horn, which is the same feed horn we use for the moon bounce. We do the EME moon bounce contest in the fall, and so it's actually right now that same feed horn. We can detect pulsars with that at those frequencies, and we also have used the 1420. The 1420 we use for hydrogen as well as pulsars and other experiments. On the software side, everything here runs in Linux. Murmur's been mentioned. It's a great tool. It runs under Linux. I use the Wine emulator to run Murmur under Linux. I also use Stellarium to plan the observations. I use the ATNF database from Australia to generate a .par file, which has the ephemeris for the Pulsar. It tells the software exactly what time to be looking for the pulse, and it has the dispersion measure and all the published values. We have our own dish control software for the pointing and tracking. It was done by a group in-house. It's excellent, works very good. And so we set up, we set up a target pulsar, we point to it, start tracking, and then I turn on all the pulsar software. We have a software spectrum analyzer for looking for RFI, a GNU radio filter bank. It originated with Marcus Leach, and then we got ours from Joe Martin, K5SO, that he had simplified it quite a bit. I got it and I simplified it a little bit more, and I converted it to Python 3, so it run with Ubuntu 20, and I also just put a wrapper around it, so it's all scripted right now. We're using the current version of Presto with Tempo for pulsar detection, and also using the current version of Riptide. That's available on GitHub. And there's some miscellaneous utilities, SIGPROC and WattUtil and some others. This is the methodology. I collect the data. I've tried RFI masking, but we don't have that much RFI, so RFI masking doesn't make much difference on the data I have. Over on the right, when I run Presto, I run the prep fold command and give it the period and derivative. But then actually I'm using the .par option, so this is all automated, and it generates the Presto plot. In the middle, as I said, to run Riptide, it needs a de-dispersed time series. So I use the Presto tool called prep data. Since I have a single subband here, I use prep data, no bury, because we're doing everything in topocentric coordinates. And I give it the dispersion measure, and then I run that resulting time series into Riptide, and I get the plots we've been looking at. Riptide will work with either Presto or SIGPROC de-dispersion. So I did also try SIGPROC de-dispersion. It's older, it's slower, and I found that it didn't work as good. SNR would be a little bit higher, and sometimes these would be darker. So I really won't spend any time on the SIGPROC version. So I do want to show some comparisons now. This is back to the earlier one where early on I showed an example of 835-41, just some noisy data. And this is what the pulse looks like once we process it through the software. It's actually a nice pulsar, good strong SNR 12.7. You can see all aspects of the Presto plot look good, and Riptide shows a very good strong pulse also in the phase and in the profile. And they have a close agreement on the period. So, starting to run these, I started building up confidence that Riptide works, and I'm starting to understand it, as well as Presto. Presto is, there's a lot going on. It takes time to learn Presto. Here's another pulsar. So all the pulsars from here on out are ones we've collected in Haswell. This is J0437-4715. It turns out it's the closest and brightest millisecond pulsar. So its period is 5.75 milliseconds. It's a very fast one. It is the fastest one that we've collected. So Presto did good on it. You can see the various aspects here that Presto is fine. And also the Riptide plot looks good. And mainly I check to make sure that the periods are both correct. So here's another one, B20, 20 plus 28. Happens to be a double peak pulse. It's called mode changing because there's a double peak and it switches back and forth. And so that's something that the physicists are working on models to understand how the peaks in this, these very intense magnetic fields on these pulsars can generate these. But This is the data we see. Here, the SNR was 4.8, so it's getting down below 5, and yet Presto still shows acceptable results. You can see the phase trace, you can see the pulse profile, the P and P dot, and just as well, Riptide also finds it, and both with very close agreement on the period. It's interesting, and I don't know why, but as you look at the data, you know, for about the first 9,000 seconds, it's hard to see any phase here. At the end, you start seeing the phase trace. Well, the same thing here. We have to go down, you know, for the first 9,000 seconds, not much, and then towards the end, you start seeing the pulse. So that's just how it is with scintillation and how the data is sometimes on pulsars.
Go to sort of the final subject, interferometry.
Okay, any questions on pulsars? I know that Ushpeeler and DSES does pulsars regularly, and it is a challenge to set up, but the biggest challenge is you need a big dish, and so DSES has one. Anybody, we do offer anybody who wants to try out their equipment, you can go arrange with us to plug it in down at Haswell and let you go search for pulsars with your equipment if you want. So that's an option for anybody who wants to travel to Colorado some weekend. Any other questions on pulsars? Okay, and I think the last section is interferometry. So a couple good report on interferometry from Wolfgang again, and we'll go into that and then we'll wrap up.
The basic principle is that you have two antennas and you analyze the signal coming to the two dishes or whatever the antennas are with respect to the relative phase. And the phase between the two signals changes as the object moves. So if it's, let's say it's right in the middle, you have the same path lengths and they are in phase, and then as the thing moves over, the phase changes. And that has a great benefit when observing continuum sources. We've seen the problems that you have with a single dish. The benefit is that a phase change is, your intensity may vary, but that doesn't affect the phase. So you're essentially much more sensitive to continuum sources. And of course, where the professionals go in, they want to achieve high spatial resolutions when they use aperture synthesis. So they effectively combine it in a way that the two dishes are separated, so simulating a big dish, so improving the spatial resolution. But I think even the higher sensitivity for continuum sources is something that is very, very valuable. Now, the point is, it works only for compact sources. It does not work for hydrogen. This is the reason why you don't get any survey with a high resolution hydrogen map, which is generated by interferometry. The best high resolution maps for hydrogen that you have is with the big single dishes like the Effelsberg 100 meter. I would like to show you two practical implementations. One is by Jim Abshir, who uses two 3-meter dishes in the L band. And this is a phase switch interferometer. Unfortunately, he does not specify, at least I couldn't find it, what exactly the baseline is. My estimate from the size of the dishes in this photo is it's about something like 10 to 15 meter. And another one example I would like to show is from our own observatory. These are two standard TV dishes with a KU band modified LNB. The modification is simply that these are externally clocked. I mentioned that you can externally clock these, and if you have two of them, you can feed them from the same clock. In this case, it was an analog correlator, and it's a baseline of 10 meter. So these are the setups they are in principle not that complicated. And the result that Jim has shown, it was on the SARA forum, so I picked it up from the SARA forum, was that, let's have a first look at the graph here. That's a single scan, so you can see just a little bit that it's going up and down, so you have a correlation there. Then if you repeat the scan, you can average that, you get a nice and clear signal, and this is then low pass filter, so taking out a little bit the high frequency noise. Now the good point here is, if you look at that, that's 23 Jansky, and I mentioned earlier in the talk that doing that with a single dish of that size, it's not practically doable. That would be even below a typical limit from a radiometer equation. Okay, he's created this graph here. This is sort of the intensity over the intensity of the fringes over the rect ascension, in this case expressed in sidereal time, and the declination. So when you move in the declination up, the source is gone, so you don't see that interference pattern anymore. And then when you're at the right declination, it shows. So this is sort of a picture of this source of only 23 Jansky. So it's a very nice experiment and just shows the capability of interferometers when it comes to compact continuum sources. The other example is the KU band interferometer. This is a not a complete sky scan, but a large part of the sky. The right ascension again, shown here, and the declination. So what has been done is these two dishes, show them again. These dishes here, they can be controlled vertically. They cannot be moved in azimuth, but they can be controlled in elevation. So the scheme was to do 1 or 2, maybe 3 days in one elevation, so sort of writing one line and then doing that. That took quite a while to cover that from -30, that's sort of the limit that we have, and then going up to 40-some degrees in declination. And the colored depicts the intensity of the fringes observed. And then there's a gap. This is simply because that satellite interference there at that elevation, so you can't do any reasonable things there. As you can see, there are a couple of sources which are well known: Omega, Orion, Crab Nebula, W451, Cygnus A. They show up. And then there are a number of dots, and we're hesitant to say these are sources. They do repeat, but we are not 100% sure because we can't identify the source that should be behind it. So this is still an open question for us whether these are artifacts or whether these are real. But in any case, think about it. This is with just 1.2 meter dishes in the KU band, where the emission of these sources is not very strong. They decline over to higher frequencies quite a bit, but you can still see the sources there on the sky. So what this is supposed to demonstrate that it is really worthwhile, once you have done all the other stuff, maybe to consider to go to interferometry if you're interested in sources, continuum sources.
Okay, that is the end of my recaps. And hope you guys enjoyed that. And all the presenters did very well. And you go back and look at the YouTube channels, you can get details on everybody. And also highly recommend looking at Ed's intro to radio astronomy YouTube thing as a starter, because it gives all the theory and stuff on most of this stuff. Okay, sort of open forum now. Anybody got any questions on any of the stuff? Go ahead, Alex.
Hold on a second. Let me see if I can unblur the background. I have a technical question I'd like to pose. When I first built my antenna, I found that well, this is a full wave loop, and it's 50 ohms here and it's 50 ohms here. The current goes out in this direction, and this is the orientation for the long 1 meter axis of the antenna. Turn it this way, you get nothing. Okay, so the feed point is in line with the long axis, the 1 meter length of the parabola dish. The patch antenna is really strange. This is the feed point here. It's 40% up from the center, gives about a 50 ohm impedance here, 40% up. However, the low impedances are on this axis, go across here. That this is the orientation for the patch feed. And I just wonder if anyone has done an NEC analysis of this plate or patch, because I can't do it. And it'd be interesting to see what the current pattern distribution is across this, because they are dramatically different in their orientation.
I have no information, but I was trying to find some web link for that patch antenna. It comes from CC, is it ERA? But they're having web problems. Is that true?
I don't know about that. I mean, I designed this. This is my design. So I mean.
Oh, I'm sorry. Okay,
yeah.
Pardon me. I'm still interested.
I mean, they all look the same.
Very good.
Right? But I mean, but the dimensions are what I designed.
But it seems so much simpler to create, and I keep pushing for simplification. Is it a common thing to go look for patch and I'll find a calculator that way, or what?
You can find square patches, and then on another page you can find somewhere that shows you how you turn a square patch into a circular, but if you want 21 centimeters, it's 100 millimeters in diameter.
And why do you say you can't do it in NEC or yourself? Or?
I have 4 NEC2, and I tried to create a network, a surface, and the currents just didn't show up at all. I just wasn't able to.
And you haven't found any examples that other people have done?
I searched, and I could not find anyone that showed any type of a current distribution across that surface. And it would be interesting to know what that is.
I've been working with it recently a little bit, and I've got a lot of examples. I'll look through there and see if I can find some that somebody else has done.
Yeah, if you could find that, it'd be interesting to see. In fact, I even did something as simplistic as I took an 1/8 watt resistor and on a plastic rod and ran around this surface and found that, yep, these are the low impedance areas and these are the high impedance areas. And so I kind of very crudely confirmed that this is the axis for the radiation, or the orientation for the paragrid.
So Alex and Bob, for the people who don't have a clue what you just said, can you simplify why you're measuring it and why that patch antenna is better than your little circular one general? Why you're even doing it?
I have found they are, at least at this point, I have found they are identical, but it's a little easier to tweak the center frequency on this by adjust. This is still in real experimental stage, but I can adjust this spacing, and the spacing here, I can do this more easily than I can just the spacing on the loop, and this determines the resonant frequency. The closer you are, the higher the frequency, and then so you can get close, and then you can tweak this spacing. So Ted, this is a a 5-inch, what is it? Daddy-O's cake pan, 100 millimeter diameter piece of copper, spaced about 8 millimeters from the back, and it's just a one of those chassis feed-through connectors. If you hold on a second, I'll show you the rest of the secret.
Alex, can I ask you a question?
Sure.
When you made this, do you have machinist skills, or
Yeah.
I don't mean the cake pan, I mean the copper. Did you make it yourself, or did you have somebody make it, or?
Well, the copper's only 1 millimeter. I mean, I just cut it on a bandsaw and then filed it. But yeah, I'm certainly not a skilled machinist, but I have a small lathe and drill press and a little benchtop milling machine, so I can do some of this stuff. Oh, what I was going to show you, only because I was concerned about ESD, is I just built a little inductor in the center, and I haven't figured out how to attach it properly. But this goes to the center. The center of this disc is like 0 ohms, so it doesn't affect the performance, but it'll provide a grounded, basically it'll ground the patch instead of having it open, as does the full loop.
Does the thickness of the copper material matter?
No.
Yeah, that's what I thought. Okay,
No,
so it's just the radius distance where your connector is, and then the spacing to the pie plate.
Right. So it's about 8 millimeters spacing to the pie plate. This is off about 18 millimeters from the center. And what else? You just don't want it to be really flexible. You want it to have some rigidity. Either, I think it's 3/32, either 0.8 or 1 millimeter is a nice, gives you a nice solid plate piece of copper to work with.
Question, Alex. How did you determine the diameter of the plate?
I based it off of this, and this comes from OM6AA, has a website where they went through a lot of analysis on a dual band, a 13 and 23 millimeter dual band dish. And this was summer a year ago. I started building the first feed before I even built the antenna. And so this is scaled off of theirs. I draw a line between the dimensions for the 13 centimeter and the 23 centimeter, and I came up with this. If you look at my presentation, it shows one of these in copper PCB board, O2 brass ring. It was quite a challenge to build. I mean, I turned the standoff. You can see everything. This is a duplication of it that you can put together in an afternoon. So the fact that the 5-inch diameter worked on this, I just said, okay, let's try it with this. The one thing I did is this is 30 centimeters deep. I cut this initially to 30, and then I backed off to 18 because with the deeper dish, with the deep dish, this is really crude, but you couldn't you couldn't see the patch from the full extent of my antenna dish, and so I assumed simplistically that if the antenna parabola can't see the copper, it can't radiate to it. And so I just arbitrarily thinned this down to 18 millimeters depth. Very unscientific, or certainly not a way a double E would do it, but it seemed to work. And so these are kind of arbitrary dimensions, but I have been successful in making this 21 centimeter patch.
What is the connection between the connector and the copper?
Yeah. That was the problem. I tried to solder it, and I had a real difficult job trying to solder to this copper yesterday. It was a real bad job. So I've gone something more sophisticated. I made a little threaded. I created a little 1032 threaded adapter in brass that's soldered to the center pin. I'm not sure how. I guess with a hot enough iron, you can solder to it, but it looked really bad. And so
right now you're going to bolt it to the center conductor.
Yeah.
Makes sense.
Yeah.
In the antennas book that I have here, it says the diameter should be 1/2 wavelength. So that's about right. 4 inches should be about a half.
Well, okay, so this is 5 inches. Diane, this is 5. This is a 5 inch.
Oh, the plate.
Oh, okay, yeah, 4 inches.
4 inches.
Yeah.
Is actually a little bit long. Okay. Quarter wave for 21 centimeters is what, 1.85 inches. So
yeah, but you also
that would be 3.7. Yeah.
You might have something like a waveguide now with a pipe plan. So I've seen problems that way.
This tunes all. I can guarantee you this tunes up well. The dimensions are right. It's tweaking it to plus or minus a millimeter or so. I mean, I'm down to that point. It's not. I've got it all torn apart, but I don't think I have an analysis of this antenna right now, but it tunes well.
If you wanted,
these are good dimensions.
If you want to fine tune it, you might be able to do it by adding one more screw in your pan coming from the back and just adjusting that screw slightly, because you would change the capacitance by doing that.
I was concerned about not knowing where that point would be. Would it tend to dampen the antenna? I've seen people do that. What I've been trying to do right now is just shift the depth of these little nylon standoffs, and I've just been putting in little spacers in here to try to shift the dimension. So this is still, in design phase, but it's close. I mean, I had it out the other day, and it nailed the old feed. So I was actually trying to see if I could get this better than the original. So I mean, if you want to build it and it works well, these, I think there's 103 millimeters in diameter, but.
All right.
Exciting, Alex. That's what we want. A real cheap feed. Easy to make. Thank you.
Yeah, it is inexpensive. Thanks.
That is good stuff. Anybody else got any other stuff they want to talk about?
Yeah, I got a question. I wanted to ask, it was mentioned that you can't use interferometry on the 21 centimeter band. Is there any more data on that? Because I got a couple of I think, what are they called? Horn of Plenties that I built and got them about a half-mile apart. Well, I'm planning on putting them about a half-mile apart and using a simple radio astronomy from Marcus to try and analyze it. And he's got a thing in there where you can use interferometry. I was going to use the 21 centimeter band, but I've just heard that you can't use it on hydrogen. Is there some reason why hydrogen won't allow you to use interferometry?
It appears to be an extended source, and even I think you have trouble with the sun sometimes with the interferometry, because it's too wide. Hydrogen's a big wide source in the sky, and that's why he's saying continuum, objects. If you go to Wolfgang's talk, I think he has I didn't put it in this thing here, but he has a lot more information on why not to use it.
My understanding is sources like Cassiopeia A and stuff are more point sources, and they are lower. They emit stronger at lower frequencies. But yeah, give it a try. I think it's just you're trying to do interferometry on a fuzzy object, all that hydrogen. It'd be fascinating to see what you get.
Okay, because I'm able to correspond just with one feed horn onto various different galaxies as they go by in the Virgo cluster. So that's why we're thinking, I get a peak, and I get a pretty good peak with each of the galaxies they drift by, which correspond, by just looking at the atlas as they go by in local side real time. So that's okay. So basically, the problem is in not having a point source or not having a distinct peak above the noise. That would be the problem.
Are you seeing far galaxies, or are you just seeing the galactic plane locally go by?
No, and I'm picking up galaxies. It's very distinct. You can see it.
Impressive.
Right. So we've done using equipment set up for the hydrogen line. You can point it at SAG-A, for example, and have decent results, interferometric results.
Awesome. Okay, thank you. I'll give it a go. Yeah.
Yeah, there's a.
Thank you.
My son presented a paper at the SARA conference in Green Bay, maybe 5 years ago, where this is described. I don't have all the details.
Okay, great.
Okay, that's very encouraging. Thank you.
Yep.
What kind of setup do you have that you can see galaxies?
It's there's two. Well, but you're looking at SAG-A, right? So, we were looking at we were using a 8-foot dish at one end of the interferometer and a 10-foot dish at the other, and they were separated maybe 30 meters. And the feed horns, the whole system was centered around looking at the hydrogen line, but we were successfully looking at SAG-A without any trouble.
Great.
And then the mixer was just cable TV splitter running backwards. So it was rather surprising to see this happen with such simple equipment. But
what did you use for your timing source?
We didn't need to, because it was a hardware mixer. We didn't have to synchronize. It was just a matter of running equal length cables.
Okay.
And the TV splitter was good enough for the 1420 megahertz?
Yep.
Encouraging.
Yep. What else? We had preamps on the feed horns. And filters appropriate for the hydrogen line. We were using what kind of SDR? Who knows? An AirSpy SDR, and regular RG6 cable. The cheapest low loss cable we could find, which was a mismatch. In 75 ohm to 50 ohm mismatch into the SDR, but it was sensitive enough to do the job. Anyway, so don't give up just because you can't see interferometry on a diffuse source. I'm sure there's plenty of things you can take a look at with your gear if you can re-aim it.
Yeah, it's very encouraging, because I also had preamps and filters and stuff like that on just a single feed horn. I was very surprised to see the peaks that I saw as stuff was drifting by. So yeah, that's very encouraging. What you're saying. I think it would be possible. Okay, I'll give it a go. So thank you very much.
Yeah. One more thing. Did we look at the sun with this?
I don't remember. It was 5 years ago.
Yeah, it was quite a few years ago, but I'm not sure if the sun radiates much in that band, but that might be an easy way to do your setup if you're just looking for an obvious target.
I did get the sun. But I use a sort of a different thing, just looking at sort of just response when I point it to the sun and when I don't point it to the sun, sort of thing, and very rough. But if I try putting it and watching the sun drift by, it's a it's not really a peak. It's just sort of a mound. You know what I mean?
Yeah. I don't know if it's enough of a point source to make the interferometry work. So
I don't. Yeah. Okay. I understand what the problem is. With a half-mile separation, you've got about a minute of arc that you can get it down to. With interferometry working.
Yeah, half mile's nice.
Yeah, I've got some farmers' fields out here in a cooperative farmer and flat land, so it makes it nice.
Yeah. Here in Vermont, nothing is flat. Even in our 30 meters, we've got probably 5 meters worth of elevation change.
And the lower one is
yeah, the lower one's sitting on the septic mound, so get it up in the air, but not quite high enough. Anyway,
here in Alberta, we can get 24 miles of flat land. So
nice bicycling. Okay, I'm gonna shut up here.
Thanks, John. Hey, Bruce, Bruce, what kind of a system do you have?
Oh, I've got I've got the old Horn of Plenty. I made a couple of those things, and I've got a filter and preamp, and it's something called Razdor, which I got from Marcus, and I'm just plocking it into there. I've got one frequency converter, and I got to get another one, so there's actually 2 feeds, so I don't have to mix them. Each horn goes into a separate feed, into the converter that's inside the box, and then that goes into whatever the software is or hardware that Marcus has put in there that will generate something out, which goes to simple RA, which is the software that was used that I'm using. And yeah, I'm quite satisfied with it. I just have to get myself another converter for the other line feed coming in.
Is your Horn of Plenty, what's the size of that? I'm not as familiar with the
roughly
dimensions.
4 feet by 4 feet by 4 feet, roughly. It's about 4 feet wide by about 3.5 feet, I think what it is, the dimensions at the face of it. And it's about, roughly 4 feet long going down into a cone. And surprising thing is that there's no, actually, you know how you have an extension on the horn sort of thing? This one doesn't have an extension, it just goes straight down with a cut off to it. Which is the way it was designed. Forget the name of the chap who designed it, but it's a brilliant design. It works great. And you know, I tape it up, you know, with conducting tape and so forth to stop all the leaks in it and so on. And remarkably sensitive, remarkably sensitive. You pick up people walking in front of it, for example. You know.
Nice. Anybody have any questions for Bruce or John or any of the team there?
I have a graph of the new patch antenna. If you want to see this, I'll share the screen if you want to see it.
Go ahead.
Let's see. Gotta find it.
And Ted, is that a Horn of Plenty that you're showing on your screen?
I guess I call it a 4-sided pyramidal horn. They're different names. I want to look up what Bruce there is talking about.
Okay, go ahead, Alex.
Did that work? Do you see it?
Yeah, I see it.
Okay, so the patch actually looks better than the loops, but I think that's because I repositioned the antenna, and only a few degrees makes a big difference in the amplitude. But anyhow, the patch with the dimensions as I showed works. So there's the 2 loops are here and the patch is here. But like I said, I think I got lucky and moved over 2 or 3 degrees, and that's all it takes when you're looking one of the hot areas of the Milky Way to gain some more amplitude. So now I got to figure out how to get back. Stop sharing.
Great. Okay. Anybody else? We're about ready to wrap up here. Thank you for this is my recap of observations. We didn't get them all, and I didn't get the detail that everybody has in their presentations, but hopefully that gave you a sample of the kind of amateur radio capabilities from this group. And I think contact the authors if you want more detail, because there's a lot of extensive knowledge in this group. All right. Any last words? All right. Thank you very much. And I'll try to get this video up here in the next couple of days. Thank you.